Hi, everyone. Thank you for joining us today for NASA's Software Spotlight webinar. I'm going to go ahead and get started. Just a reminder that this webinar is being recorded. My name is Hia, from NASA's Technology Transfer Program, and I'll be your host for this session on chemical equilibrium with applications in MATLAB. Featured in NASA's newly released software catalog, this software provides advanced modeling of chemical equilibrium and thermodynamic behavior for high-performance systems. Our presenter today is Chip Kopicz. Chip Kopicz is the Components Design and Test Support Task Lead on the ESSCA contract supporting Marshall Space Flight Center's ER-13 Components Development and Technology branch and working with combustion devices for 25 years. Over the years, he has worked on numerous component programs, engine systems such as Integrated Powerhead Demonstrator, J2X, RS-25, Cobra, and the SSC A3 test stand. Before joining the ESSCA contract, Chip worked various aspects for Space Station and designed the X-43A, HyperX airframe, and inboard profile. And with that, I'll turn it over to our presenter, Chip Kopicz.
Thank you. As mentioned, I'm going to be presenting chemical equilibrium with applications in MATLAB. This is not a MATLAB wrapper for the Glenn Research Center FORTRAN CEA code. This is a complete rewrite of the FORTRAN code into MATLAB. So if you want to get a copy of this software, you can go to the software catalog, type CEAM in the search box, it'll pop up. If you happen to be a civil servant, it's snap download. Non-civil servants will work through that. This was once restricted, but it's no longer. Provided in download is a P code, a P file of the code, a help file with a .m extension, a thermodynamic library which can be opened and viewed. There's a quick start slide package. There's a standalone executable application, and there is a Python package compiled with it. What I don't have noted on here is there is also a graphical interface that can be run as a separate, as an independent program, and it can also be run as an application within MATLAB. CEA for MATLAB, we expanded some of the units for input and output. So we include English units, MKS, CGS. We also have the default units that the bar and PSI that the CEA works with. This can be called from, the results can be called from script. The program can be called from script. The output is always written to a structured array and immediately available for calculations. There's also an option to write the file, the output to a text file, and to write it to the screen, or it will do both. The interface was designed to, as best we could, sort of carry over on the input from the FORTRAN deck. So here we see an example of the FORTRAN CEA FORTRAN input deck, and converting that, we give an output. We give it a variable we'd use for output. Say that's equal to, call the function CEA, open the parentheses, and that's where we begin. With that, we separate everything in the output FORTRAN output deck with a comma. Come back and encase all of the words within the single quotes that you see in MATLAB. That turns into the magenta color. Then we close the parentheses, add a semicolon so it doesn't print to the screen by default. And then at this point, you can execute the code and get results. So as I showed, it's called with an output variable is equal to CEA and the user-defined inputs. output variables, whatever the user wants it to be. CEA is a case-sensitive call. User-defined inputs are going to vary for the applicable data sets. The mandatory data sets are reactants. What's going to be burned? What information? And the information that goes with that. The problem. Which problem? Do you want a rocket problem, a point problem, a shock problem, or a detonation problem? And the options that go with that. And finally, you have to put something at the end so that the code knows we're done giving it inputs. There's an option for to add outputs, and that gives options for trace, a trace limit, identifying mass or mole fractions, the unit system you'd like the output provided in, and then short, the debug short or not for handling information, trying to debug any problems on the run. Data sets can be entered in any order except for end, which has to be the last thing. So you can identify reactants first, tell it the type of problem, or you can start with the type of problem and then do the reactants. And all the data entries are comma separated. Reactants contain the type of reactant. Is it a fuel, an oxidizer, or you can go by name so that you just simply list what the reactants are in percentages. The name of each reactant, hydrogen or methane, and the chemical formula, the amount of that reactant for mass or mole, the amount of each reactant with respect to that type of reactant, 20% fuel or 30% ox, etc. Specific information to that reactant, its enthalpy, its temperature, or its density. In the event of a duplicate input between the problem data set and the reactant data set, the reactant data set input will be used and the problem data set is going to be dismissed. The problem contains the type of problem, the bulk properties, and the bulk property inputs that vary the type of problem that will be addressed in a later slide. And then end marks the end of the input. Units accepted as input. Temperature. Its keyword is T. The CEAM will accept all 4 temperature scales as input. Energy. There's enthalpy with a keyword of H. Internal energy, a keyword of U. These are in units of energy per mass. So the energies that can be used are listed here. The masses that can be used are listed here. Normally we think of BTU per pound mass, or joules per mole, or joules per kilogram. We have checked if you want to mix it so that we do BTUs per mole or BTUs per gram and mix up units. It can be done. It will be handled, but it's going to be on the user to properly translate or provide the correct numbers on the input. As far as, this is how many BTUs per gram our energy is. The enthalpy can, as heritage input, can also still be entered as H over R, where R is universal gas constant in metric units. Entropy is S. This is energy per mass per temperature. I've shown you all those acceptable units on the previous slide. And it can also be entered as S over R. Density has a keyword of rho. Typo here I'll have to fix. The units are mass per volume. The acceptable masses are shown here. The acceptable volumes are shown here. And these are the units that MATLAB is looking for, our CEAM is looking for. Specific volume is volume per mass. Its keyword is V. And they still use the same volumes and the same masses. Pressure, that keyword is P. And then these are the pressures that we've taught CEAM to recognize and convert for the calculations. Within the rocket problem, you can define a finite area combustor. And one of the ways to define a finite area combustor is a mass flow per unit area in seconds. Well, a mass flow per unit area. So it'll be like kilograms per second per centimeter squared. So, but in this case, we have, here's the acceptable masses, here's the acceptable areas, and the time was always going to be expected to be seconds. Shock problems have two inputs. Mach number is dimensionless. Velocity does. So for velocities, again, we're looking for a length per time. The time's always going to be seconds. And the length is going to be, these are the acceptable lengths that CEAM will recognize and convert properly for the calculations. When it comes to the output, these are the unit options. The keywords for the to identify them are identified here in the first row, and then these are the properties with the associated units that go with them. CEAM works all of the same problems that CEA does. So we do the point problems we see here, solve a rocket problem, we do the shock problem, and we do the detonation problems. Point problems may be identified as TP or PT. Order doesn't matter. However, if you identify it as TP as the problem type, then it's expecting the inputs to be in the same order. So TP, give it a temperature first, then a pressure. If you identify it as PT, give it a pressure first, then a temperature. Shock problems are based on shock tube calculations. These are not external flows over surfaces. And as such, the reliability of these calculations is good up to about Mach 10. And we find that beyond Mach 10, it's heavily dependent on the reactants, how good or consistent it may be. But we strongly recommend, if you're looking to try to do planetary entry or anything over Mach 10, you need another code to begin to calculate it. Detonation problems are Chapman-Juke calculations. We have users that use CEAM to do fluid properties. This is a typical way to set it up. A problem, typically looking for, we can identify a temperature and a pressure that we want things provided at. Identify the pressure and the temperature. Here we give an OF to 0, and with the reactant fuel, you give it that. Now this is with this reaction with no oxygen, CEAM will return the properties of CH4 at the identified pressure and temperature. And so when attempting to do this, calculate the properties, set the ODF to 0, it'll get it. It'll say oxidant not permitted when specifying 100% fuel, but if I don't give it an oxidant, then it tends to crash. So we'll take the warning and ignore it. But we've been able to verify this against the FORTRAN CEA code that we're returning consistent results. We do say avoid the conditions where property changes would be within or cross over the melting point or the boiling point, because the latent heats are not accounted for in these in the thermodynamic libraries. These are all given pressure temperature type. These are all specific calculations, not accounting for all of the thermodynamics. The mixture ratios that can be identified are shown here. Only one type of mixture ratio can be identified per problem, but you can run many mixture ratios per problem. So I can have to pick one, I pick an O to F, but then I could run 20 O to F conditions with one problem run. When it's done, the output's going to be written to a structured array. The structured array can be opened either by typing the name in the command line or by double-clicking on it in the workspace. And then the field of greatest interest are probably going to be in the output. See, so your output variable will appear here in the workspace. Double-click on that, and we'll see, here's the version that we're running. Here's the timestamp for when it was run, the original author. Here's the output, and for the record, we do write the input parameters that were provided for the problem run. When we get into the output, we'll see the output calculations. We can pick the equilibrium results. Here we double-clicked on a gamma to see two gammas. We showed the command line. In this case, when this problem was run, our output variable on the output call was x. We say x.output because that brings it to the output section of the structured array. Equilibrium, the QL for the equilibrium, dot gamma, and it returns on the command line the same values of gamma. The CEAM executable file is a standalone application in a zip file. It does require the installation of a runtime version of MATLAB. There's some instructions on how to run it. An input example, if this is what it looks like to run the problem within the MATLAB, what we need to do is essentially eliminate all of the punctuation for the executable file. Simply list CE, and here we're calling the executable file CEAM. So we're using CEAM instead of CEA. And then we list every piece here spaced eliminated, with the exception of the pressure, and if we had it, temperature, so that it would know that I'm looking for pressure, because it's still looking at these things with connected, no spaces. Every time there's a space, it's taking it as a different input. So P comma PSIA is needed to match what's inside the single quotes here, so that the code will properly interpret the input when it's running it. We followed the instructions within MATLAB to compile the code for Python, hoping that maybe we did it right, and somebody that knows Python better than we do. We just ran out of time, shall we say, to actually figure out exactly how to make it work. But if we get there, future revisions, we'll add instructions on how to. We can add explicit instructions on how we got it to work with Python. There is a GUI. It will have there's a drop-down menu here that will allow you to select the different problems. A case box to name the case that's being run. Select the input fractions, mass or mole fractions. Choose mixture ratios, units, temperature unit, and then with this, it's showing these boxes will then begin engineering. This will change to default here. The chemistry defaults to equilibrium. And then if there's a rocket problem, there's a chance for a finite area combustor. It'll give you a choice of picking contraction ratio or flow rates. Select reactants over here. They'll appear here in this box. And then when the reactant appears here, it can be double-clicked on and edited, and then also saved to if you have a custom setup you want, you can save that it will save that to a separate library for use later. Depending on the problem selected here, these input boxes will change. Point problems, there'll be 2 boxes up here that'll be labeled appropriately. If it were pressure and temperature, it would just be these 2. Enthalpy and temperature, right? Enthalpy and pressure, whatever, it will change these. This obviously captures all of the rocket input problems, and we did add some calculations in here. So that if an altitude's provided, we'll use a 1976 standard atmosphere to get that pressure and calculate the ISP at the exit plane of the nozzle. And then we can select activate ions, trace elements. Once the reactants have been identified, if you want only or omit, by clicking one of these, a second list will appear over here showing the products that are available to either include only these or omit these, and if necessary, insert. Editing the reactants by clicking it. You can click new reactant or edit reactant. The new reactants will come up. It will show the chemical formula, the names, whether it's identify fuel or oxidizer. You can enter an enthalpy. It takes a reactant type for fuel or oxidizer. So if you have a need to redefine one, to redefine something as an oxidizer instead of a fuel, you'll have the option to do that. And then there are cases where it comes to an option to reset everything to match the thermodynamic library, and it gives appropriate warnings when you go to do that. The output, the top of the window will give the command line for the problem based on the GUI inputs, and then the screen printout will appear here in the window that has a format very much like the Heritage FORTRAN code. And then to the right, you can pick the output files, the output variables, click on those. We can add them to X or Y or to Z to make 2 and 3D plots when a sufficient data is available to give a sense of how things are changing for each problem or across the problems that have been run. The plot window here may be extracted to separate windows. And if you rerun a different problem, the extracted windows don't automatically close or update. They would have to be closed each time. Okay, that covers all the features. And the backup slides are just show some generic formats of the different point problems and the different problems that can be run.
Thank you. That was super insightful. Thanks for walking us through that. I did receive a couple questions by email. If anybody else has questions, also feel free to type them in the chat. So we're almost at time, but and Chip, I think you may have covered this question already a bit, but just to clarify, is CEAM compatible with other simulation tools or environments, and how simple is it to export data for multi-tool analysis?
I guess that's going to depend on the end user and how well they know each code.
True. Yeah.
And the data, like I said, the data itself can, through MATLAB and selecting that data, can be written out to individual variables. A lot of the times we working within MATLAB completely. So I haven't had any experience of trying to bring that data into something else, except maybe we did write a tool that writes all of our outputs into an Excel sheet. So when we run our, whatever it is now, 70 verification problems to try to make sure we didn't mess something up when we fix another problem, we do have one where we go back in, read the structure array, and write it to the different sheets of Excel.
Got it. Okay, thank you. And then this is more of a general question that somebody asked, what are the typical computing requirements and runtimes for larger simulations using CEAM?
When we do our, I can reference it to when we do run our verification routine, we have about 70 problems that have most of them have a lot of inputs, multiple inputs each. It takes it maybe a minute and a half to run a couple of hundred problems. And I'm probably overstating the time.
Oh, okay. Thank you.
It's pretty quick because we started this code because we were in a position where we had a lot of data, and we got to the point where we exceeded limits on our 16-bit Excel for rows and columns when we're doing our analysis. So to me, everything MATLAB does is infinitely faster than what I witnessed in Excel trying to do similar calculations.
Great, thank you. Looks like we have a new question in the chat. Are the scripts portable on a well, actually, we move on to from my understanding, the thermolib dataset can be modified from the GUI, but not using the command line manually. This person has been doing a hypergolic RDRE design and have wanted to add additional data for chemical simulations.
If you wanted to modify, because part of it is the way we wrote the code is we said this is how big the thermodynamic library is. So it only looks at the, say, 2087 items that we have in there. After that, you can completely define your own reactants within the problem call by saying, here's the name of the reactant, here's the formula, and the enthalpy and the temperature that I'd like to use. And that will always work within it. That also allows you to just say loop your problem and adjust enthalpies or temperatures for your propellants within your models.
Got it. Thank you. And then, so we're at time, but let's try to cover this last question. If we're familiar with this operating system, I believe Raspberry Pi is the operating system designed for the Raspberry Pi hardware. So, are the scripts portable on that native operating system?
I have to say, I don't know if it's portable from the Python or the Raspberry Pi.
Okay.
We just haven't, on this end, we've done what we believe is the compilation for use in Python, but we really haven't gone very far with it. My only fear is that the Python the Python compilation may require front-end code like I had to write for the executable version, and I just haven't gotten smart enough to do that, to know that for sure.